Introduction. Today we have Mr. Kashyap amongst us, who will tell you something about linear programming. Priya, what is linear programming?
I don't know. Even I'm listening this word for the first time. Okay, listen.
Students, linear programming is the process of taking various linear inequalities relating to some situation and finding the best value obtainable under those conditions. Sir, can you give us an example? Sure. A typical example would be taking the limitations of materials and labor and then determining the best production levels for maximal profits under those conditions. In real life, linear programming is part of a very important area of mathematics called optimization techniques. If you are interested in this topic, then I can teach you this in detail. Yes, sir, please teach us. Okay, let's start then. Objectives. At the end of this lesson, you'll be able to understand linear programming problem LPP, learn mathematical formulation of the problem, explain graphical method of solving linear programming problems, explain corner point method, learn different types of linear programming problems. Terms evolved in linear programming. Objective function. In a linear programming problem, Z, the linear function of the variables which is to be optimized, is called objective function. Here, a linear form means a mathematical expression of the type a1 x1 plus a2 x2 plus so on till plus an xn, where a1, a2 and so on till an are constant and x1, x2 and so on till xn are variables. Variables. In linear programming problems, the products, services, projects, etc. that are competing with each other for sharing the given limited resources are called the variables or decision variables. Constraints. The limitations on resources like cash in hand, production capacity, manpower, time, machines, etc., which are to be allocated among various competing variables, are in the form of linear equations and are called constraints or restrictions. Non-negative restrictions. All decision variables must assume non-negative values, as negative value of physical quantities is an impossible situation. Linear programming problem, LPP. A linear programming problem is one in which we are to find the maximum or minimum value of a linear expression, ax plus by plus cz plus and so on, called the objective function, subject to a number of linear constraints of the form ax plus by plus cz plus and so on till less than or equal to n, or ax plus by plus cz plus and so on till greater than or equal to n. The largest or smallest value of the objective function is called the optimal value, and a collection of values of x, y, z and so on that gives the optimal value constitutes an optimal solution. The variables x, y, z and so on are called the decision variables. Mathematical formulation of the problem. The formulation of linear programming problem as a mathematical model involves the given key steps. Step 1. Identify the decision variables to be determined and express them in terms of algebraic symbols such as x1, x2 and so on. Step 2. Identify all the limitations in the given problem and then express them as linear equations or inequalities in the terms of above defined decision variables. Step 3. Identify the objective which is to be optimized, maximized or minimized and express it as a linear function of the above defined decision variables. Example. A retailer wishes to buy a number of transistor radio sets of types A and B. Type A cost Rs 360 each and type B cost Rs 240 each. The retailer knows that he cannot sell more than 20 sets, so he does not want to buy more than 20 sets and he cannot afford to pay more than Rs 5,760. His expectation is that he would get a profit of Rs 50 for each set of type A and Rs 40 for each set of type B. Formulate the problem as a linear programming problem to get the maximum profit. Solution. Suppose the retailer purchase X1 sets of type A and X2 sets of type B. Since the number of sets of each type is non-negative, so we have X1 is greater than or equal to 0, mark it as 1. X2 is greater than or equal to 0, mark it as 2. Also, the cost of X1 sets of type A and X2 sets of type B is 360 X1 plus 240 X2, and it should be equal to or less than Rs 5,760. That is, 360 X1 plus 240 X2 is smaller than or equal to 5,760. Or 3x1 plus 2x2 is smaller than or equal to 48. Mark it as 3. Further, the number of sets of both types should not exceed 20, so x1 plus x2 is either smaller than or equal to 20. Mark it as 4. Since the total profit consists of profit derived from selling the x1 type A sets and x2 type B sets, therefore the retailer earns the profit of Rs 50 x1 on type A sets and Rs 40 x2 on type B sets. So the total profit is given by Z equals 50 x1 plus 40 x2. Mark it as 5. Hence, the mathematical formulation of the given linear programming problem is as follows. Maximize Z equals 50 x1 plus 40 x2. Subject to the conditions, 3x1 plus 2x2 is smaller than or equal to 48. x1 plus x2 is smaller than or equal to 20. x1 is greater than or equal to 0. x2 is greater than or equal to 0. Sketching the solution set of a linear inequality. Sketch the straight line obtained by replacing the inequality with equality. Choose a test point not on the line. 0, 0 is a good choice if the line does not pass through the origin, and if the line does pass through the origin, a point on one of the axes would be a good choice. If the test point satisfies the inequality, then the set of solutions is the entire region on the same side of the line as the test point. Otherwise, it is the region on the other side of the line. In either case, shade out the side that does not contain the solutions, leaving the solution region showing. Example. To sketch the linear inequality, 3x minus 4y is smaller than or equal to 12. First sketch the line 3x minus 4y as 12. Next, choose the origin 0, 0 as the test point since it is not on the line. Substituting x as 0, y as 0 in the inequality gives 3, 0 minus 4, 0 is smaller than or equal to 12. Since this is a true statement, 0, 0 is in the solution set, so the solution set consists of all points on the same side as 0, 0. This region is left unshaded, while the gray shaded region is blocked out. Graphical method of solving linear programming problems. Feasible region. The feasible region determined by a collection of linear inequalities is the collection of points that satisfy all the inequalities. To sketch the feasible region determined by a collection of linear inequalities in two variables. Sketch the regions represented by each inequality on the same graph, remembering to shade the parts of the plane that you do not want. What is unshaded when you are done is the feasible region. Example. The feasible region for the following collection of inequalities is the unshaded region shown, including its boundary. 3x minus 4y is smaller than or equal to 12. X plus 2y is greater than or equal to 4. x is greater than or equal to 1, y is greater than or equal to 0. The graphical method for solving linear programming problems in two unknowns is 1. Graph the feasible region. 2. Compute the coordinates of the corner points. 3. Substitute the coordinates of the corner points into the objective function to see which gives the optimal value. 4. If the feasible region is not bounded, this method can be misleading. Optimal solutions always exist when the feasible region is bounded, but may or may not exist when the feasible region is unbounded. Theorems. These given theorems are fundamental in solving linear programming problems. Theorem 1. Let R be the feasible region, convex polygon for a linear programming problem, and let Z equals ax plus by be the objective function. When Z has an optimal value, maximum or minimal, where the variables x and y are subject to constraints described by linear inequalities, this optimal value must occur at a corner point vertex of the feasible region. Theorem 2. Let R be the feasible region for a linear programming problem, and let Z equals ax plus by be the objective function. If R is bounded, then the objective function Z has both a maximum and a minimum value on R, and each of these occurs at a corner point vertex of R. Corner point method. The method comprises of the given steps. 1. Find the feasible region of the linear programming problem and determine its corner points vertices either by inspection or by solving the two equations of the lines intersecting at that point. 2. Evaluate the objective function z equals ax plus by at each corner point. Let m and m respectively denote the largest and smallest values of these points. 3. 1. When the feasible region is bounded, m and m are the maximum and minimum values of z. 2. In case the feasible region is unbounded, we have a. M is the maximum value of z if the open half plane determined by ax plus by is greater than m has no point in common with the feasible region. Otherwise, z has no maximum value. B. Similarly, m is the minimum value of z if the open half plane determined by ax plus by is smaller than m has no point in the common with the feasible region. Otherwise, z has no minimum value. Example of linear programming problem. Example. Solve the following linear programming problems graphically. Maximize z equals 3x plus 4y. Subject to the constraints. X plus y is smaller than or equal to 4. X greater than or equal to 0. Y greater than equal to 0. Solution. The feasible region determined by the constraints x plus y is smaller than or equal to 4. X is greater than or equal to 0. Y is greater than or equal to 0 is given in the figure. The corner points of the feasible region are O, 0, 0, A, 4, 0, and B, 0, 4. The values of z at these points are as follows. Therefore, the maximum value of z is 16 at the point B, 0, 4. Example. Solve the following linear programming problems graphically. Minimize z equals 3x plus 5y such that x plus 3y is greater than or equal to 3, x plus y is greater than or equal to 2, xy is greater than or equal to 0. Solution. The feasible region determined by the system of constraints x plus 3y is greater than or equal to 3, x plus y is greater than or equal to 2, and xy is greater than or equal to 0 is as follows. It can be seen that the feasible region is unbounded. The corner points of the feasible region are A 3, 0, B 3 upon 2, 1 upon 2, and C 0, 2. The values of Z at these corner points are as follows. As the feasible region is unbounded, therefore 7 may or may not be the minimum value of Z. For this, we draw the graph of the inequality 3x plus 5y is smaller than 7 and check whether the resulting half plane has points in common with the feasible region or not. It can be seen that the feasible region has no common point with 3x plus 5y is smaller than 7. Therefore, the minimum value of Z is 7 at 3 upon 2, 1 upon 2. Different types of linear programming problems. Manufacturing problems. In these problems, we determine the number of units of different products which should be produced and sold by a firm when each product requires a fixed manpower, machine hours, labor hour per unit of product, warehouse space per unit of the output, etc. in order to make maximum profit. Let's take an example to understand it better. Example. A factory manufactures two types of screws, A and B. Each type of screw requires the use of two machines, an automatic and a hand-operated. It takes 4 minutes on the automatic and 6 minutes on hand-operated machines to manufacture a package of screws A, while it takes 6 minutes on automatic and 3 minutes on the hand-operated machines to manufacture a package of screws B. Each machine is available for at the most 4 hours on any day. The manufacturer can sell a package of screws A at a profit of Rs 7 and screws B at a profit of Rs 10. Assuming that he can sell all the screws he manufactures, how many packages of each type should the factory owner produce in a day in order to maximize his profit? Determine the maximum profit. Solution. Let the factory manufacture X screws of type A and Y screws of type B on each day. Therefore, X is greater than or equal to 0 and Y is greater than or equal to 0. The given information can be compiled in a table as follows. The profit on a package of screws A is Rs 7 and on the package of screws B is Rs 10. Therefore, the constraints are 4x plus 6y is smaller than or equal to 240. 6x plus 3y is smaller than or equal to 240. Total profit Z is equal to 7x plus 10y. The mathematical formulation of the given problem is maximize Z equals 7x plus 10y, mark it as equation 1, subject to the constraints. 4x plus 6y is smaller than or equal to 240, mark it as equation 2. 6x plus 3y is smaller than or equal to 240, mark it as equation 3. xy is greater than or equal to 0. 4. The feasible region determined by the system of constraints is given as the corner points are A 40, 0, B 30, 20, and C 0, 40. The values of Z at these corner points are as follows. The maximum value of Z is 410 at 30, 20. Thus, the factory should produce 30 packages of screws A and 20 packages of screws B to get the maximum profit of Rs 410. Diet problems. In these problems, we determine the amount of different kinds of constituents or nutrients which should be included in a diet so as to minimize the cost of the desired diet such that it contains a certain minimum amount of each constituent nutrients. Example. Reshma wishes to mix two types of food, P and Q, in such a way that the vitamin contents of the mixture contain at least 8 units of vitamin A and 11 units of vitamin B. Food P costs Rs 60 per kg and food Q costs Rs 80 per kg. Food P contains 3 units per kg of vitamin A and 5 units per kg of vitamin B, while food Q contains 4 units per kg of vitamin A and 2 units per kg of vitamin B. Determine the minimum cost of the mixture. Solution. Let the mixture contain x kg of food P and y kg of food Q. Therefore, x is greater than or equal to 0 and y is greater than or equal to 0. The given information can be compiled in a table as follows. The mixture must contain at least 8 units of vitamin A and 11 units of vitamin B. Therefore, the constraints are 3x plus 4y is greater than or equal to 8, 5x plus 2y is greater than or equal to 11. Total cost Z of purchasing food is Z equals 60x plus 80y. The mathematical formulation of the given problem is minimize Z equals 60x plus 80y. Mark it as equation 1. Subject to the constraints. 3x plus 4y is greater than or equal to 8. Mark it as equation 2. 5x plus 2y is greater than or equal to 11. Mark it as equation 3. xy is greater than or equal to 0. Mark it as equation 4. The feasible region determined by the system of constraints is as follows. It can be seen that the feasible region is unbounded. The corner points of the feasible region are A 8 upon 3 0, B 2 1 upon 2 and C 0 11 upon 2. The values of Z at these corner points are as follows. As the feasible region is unbounded, therefore 160 may or may not be the minimum value of Z. For this, we graph the inequality 60x plus 80y is smaller than 160 or 3x plus 4y is smaller than 8 and check whether the resulting half plane has points in common with the feasible region or not. It can be seen that the feasible region has no common point with 3x plus 4y smaller than 8. Therefore, the minimum cost of the mixture will be Rs 160 at the line segment joining the points 8 upon 3, 0 and 2, 1 upon 2. Transportation problems. Transportation problems. In these problems, we determine a transportation schedule in order to find the cheapest way of transporting a product from plants, factories situated at different locations to different markets. Example. Two godowns A and B have grain capacity of 100 quintals and 50 quintals respectively. They supply to 3 ration shops D, E and F whose requirements are 60, 50 and 40 quintals respectively. The cost of transportation per quintal from the godowns to the shops is given in the following table. How should the supplies be transported in order that the transportation cost is minimum? What is the minimum cost? Solution. Let godown A supply X and Y quintals of grain to the shops D and E respectively. Then 100 minus X minus Y will be supplied to shop F. The requirement at shop D is 60 quintals since X quintals are transported from godown A. Therefore, the remaining 60 minus X quintals will be transported from godown B. Similarly, 50 minus Y quintals and 40 minus 100 minus X minus Y equals X plus Y minus 60 quintals will be transported from godown B to shop E and F respectively. The given problem can be represented diagrammatically. Total transportation cost Z is given by. The given problem can be formulated as minimize Z equals 2.5x plus 1.5y plus 410. Mark it as equation 1. Subject to the constraints. The feasible region determined by the system of constraints is as follows. The corner points are A 60 0, B 60 40, C 50 50 and D 10 50. The values of Z at these corner points are as follows. The minimum value of Z is 510 at 1050. Thus, the amount of grain transported from A to D, E and F is 10 quintals, 50 quintals and 40 quintals respectively and from B to D, E and F is 50 quintals, 0 quintals and 0 quintals respectively. The minimum cost is rupees 510. Did you know? The first problem in linear programming was formulated in 1941 by the Russian mathematician L. Kantorovich and the American economist F. L. Hitchcock, both of whom worked at it independently of each other. This was the well-known transportation problem. In 1947, the American economist G. B. Dantzig suggested an efficient method known as the simplex method, which is an iterative procedure to solve any linear programming problem in a finite number of steps. Summary. Let us summarize what we have learned. A linear programming problem is one that is concerned with finding the optimal value, maximum or minimum of a linear function of several variables called objective function, subject to the conditions that the variables are non-negative and satisfy a set of linear inequalities called linear constraints. Variables are sometimes called decision variables and are non-negative. A few important linear programming problems are 1. Diet problems, 2. Manufacturing problems, 3. Transportation problems. The common region determined by all the constraints, including the non-negative constraints, x is greater than or equal to 0, y is greater than or equal to 0 of a linear programming problem is called the feasible region or solution region for the problem. Points within and on the boundary of the feasible region represent feasible solutions of the constraints. Any point outside the feasible region is an infeasible solution. Any point in the feasible region that gives the optimal value, maximum or minimum of the objective function is called an optimal solution. If the feasible region is unbounded, then a maximum or a minimum may not exist. However, if it exists, it must occur at a corner point of R. Corner point method for solving a linear programming problem. The method comprises of the following steps. 1. Find the feasible region of the linear programming problem and determine its corner points, vertices. 2. Evaluate the objective function z is equal to ax plus by at each corner point. Let m and m respectively be the largest and smallest values at these points. 3. If the feasible region is unbounded, m and m respectively are the maximum and minimum values of the objective function. If the feasible region is unbounded, then 1. M is the maximum value of the objective function if the open half plane determined by ax plus by greater than m has no point in common with the feasible region. Otherwise, the objective function has no maximum value. 2. M is the minimum value of the objective function if the open half plane determined by ax plus by smaller than m has no point in common with the feasible region. Otherwise, the objective function has no minimum value. If two corner points of the feasible region are both optimal solutions of the same type, that is, both produce the same maximum or minimum, then any point on the line segment joining these 2 points is also an optimal solution of the same type.